Good evening, ma'am. Am I audible to you?
Good evening, sir.
Okay, ma'am. Okay.
Sir, you can start, sir.
Okay, ma'am. Okay. Good evening, students. Today we are going to start our discussion on moving charges and magnetism. On this chapter, we have several concepts. We will be discussing the concepts initially. After discussing the concepts, we will discuss numerical problems. Okay. So I have opened the whiteboard now. So moving charges and magnetism. So we all know very well that when an electric charge is moving, it constitutes an electric current. Okay, whenever charges are moving, we call that phenomena as the passage of electric current. Okay, so whenever electric current flows through a conductor, you will be getting magnetic field around the conductor. So this is the basic concept of this chapter or this lesson. Okay, moving charges are always associated with magnetic field. In other words, current carrying conductors, they have a magnetic field around them. Okay, so this is the core idea of this lesson or this chapter. Okay, so when you have a current carrying conductor, you can have magnetic field around it. But how to calculate the magnetic field around a current carrying conductor? Okay, so how to calculate that? Calculation can be done using Biot-Savart law. Okay, Biot-Savart law is the law used to find out the magnetic field due to a current carrying conductor. And for this, let me consider a wire like this. Okay, and the current is flowing in this direction, that is represented by small letter I. And in this wire, let me consider that I have a current element dl. Okay, dl means the length of this small portion of the wire carrying this current, and I am having a point P here. The point P is at a distance r from this current element. Okay, so here I am having a point P. Okay, so this is the point P, and this point P is at a distance r from this current element, vector r. And from this current element, you are having the angle. Okay, the angle is theta. Theta is the angle between the line joining this current element and the point P. So here, this is the whole wire. Okay, this is the whole wire, and you are having a point P at a distance r from this current element dl. Then what will be the magnetic field due to this current element dl at this point P? So that can be given by Biot-Savart law. Okay, so according to Biot-Savart law, due to this current element dl, we are having a magnetic field at this point P. So since this is a small current element, I am considering the small magnetic field produced by this small current element dB, and that is equal to k into I dl sine theta divided by r square. Okay, this is the formula for finding the magnetic field due to the small current element at this point P, dB, equal to k into I dl sine theta by r square, and k is a constant. That constant is equal to mu naught by 4 pi. Okay, where mu naught is nothing but the magnetic permeability of vacuum or free space. When you keep this current element in vacuum, then you will be having this constant mu naught. But when you keep this current element in any other medium, this mu naught is replaced by mu. So dB equal to k into I dl sine theta by r square is the formula from Biot-Savart law. So dB is equal to mu naught by 4 pi into I dl sine theta divided by r square. So this is the magnetic field due to Biot-Savart law. And when you want to find out the total magnetic field at this point P due to the entire wire, what you have to do? You have to go for integration of this dB. Okay, so when you want to find out the total magnetic field, then you have to go for integration. Okay, integral dB will give you the total magnetic field at this point P due to the entire wire. Okay, so this is called Biot-Savart law, and whenever current carrying conductor, okay, whenever there's a current carrying conductor and carries magnetic field, then you can always find out the direction of the magnetic field using different rules. Okay, using different rules. There are different rules like right hand thumb rule or Maxwell's corkscrew rule, right? Like that. Okay, like that you are having different rules. And here I want to tell you something. So this Biot-Savart law is actually analogous to the Coulomb's law in electrostatics actually. Okay, so it is analogous to Coulomb's law because in electrostatics the Coulomb's law gives you the expression for finding the electric field due to stationary charges. Here this Biot-Savart law helps you to find out the magnetic field at a particular point due to a current carrying wire or current carrying conductor. Okay, so in this way this Biot-Savart law is analogous to Coulomb's law. Now we can write the expression due to the expression for a magnetic field due to a straight conductor carrying current. Okay, straight conductor carrying current. We can find out the expression for this magnetic field, or we can write the expression for this magnetic field. And for that I will be opening a new page. So here magnetic field due to a straight current carrying conductor or a straight current carrying wire. So magnetic field due to a straight current carrying wire. So for that we can consider a wire. Okay, let me see if we can draw the wire here. Okay, this is the long wire actually. So the long wire cross section usually looks like a cylinder. So that's why I am drawing like this. So the cylindrical shape of this wire. This is the cylindrical shape of the wire, and this is the center point O. Okay, this is the center point O. From here, let me consider I have a point P. Here I am having a point P. This is the long current carrying wire. And here I am considering a current element. So small current element in the entire wire I am considering. This is represented by DL. Okay. This is represented by DL. So DL is the small element in this entire wire DL. So from the center point, this element makes an angle 5. Okay. So here this makes an element 5, or this makes an angle phi actually. So this angle is actually phi. And these angles actually from here to this point P, from here to this point P, and also from here, okay, to this point P. So these angles can be taken as theta 1 and theta 2. Okay, theta 1, theta 1, and this entire angle from here to here, it is theta 2. Then this angle you can consider as theta actually. This point P is at a distance d from this center. Okay. And here current I is flowing through this entire wire, current I. And here point P is at a distance d from the center of this wire. Now from the Biot-Savart law, I am going to find out the magnetic field. So this end is A and this end is B. Okay. So what is the magnetic field due to the entire wire at this point P? Okay. So that I am going to write now. So that is B equal to mu naught by 4 pi into I integral A to B. Okay. A to B dl sin theta whole divided by r square. Mu naught I by 4 pi integral A to B dl sin theta by r square. So from this equation you can find out the total magnetic field, and after applying all the steps here, the final result is mu naught I by 4 pi. Okay. Mu naught I by 4 pi into sin theta 1 4 pi into d actually. So here you have this d into within the bracket sin theta 1 plus sin theta 2 is the magnetic field due to this long wire. Okay, long straight current carrying wire. This is the magnetic field equation. Mu naught I by 4 pi d into sin theta 1 plus sin theta 2. This is the magnetic field. And from this general expression, you can find out the magnetic field for different cases. Okay, for different positions of the point P, you can find out the magnetic field. For example, when the point P, okay, when the point P lies on this portion of the wire, that is the perpendicular bisector. Okay, the perpendicular bisector. So the case 1, I am taking. So case 1, when the point P lies on the perpendicular bisector. of the wire. What will happen? So here the phi 1, okay, the phi 1, this angles will be equal to one another. So phi 1 and phi 2, so this angle theta 1 and theta 2, okay, here theta 1 and theta 2. So in this case both will be equal actually. So then you can see B equal to, so here in this case theta 1 equal to theta 2, so mu naught I by 4 pi d into sine, so theta 1 equal to theta 2 equal to theta, so sine theta plus sine theta, so it will be 2 sine theta. So that will give you mu naught I by 2 pi d into sine theta, okay. So here this thing is sine theta. So this is how you can find out the magnetic field when the point P lies on the perpendicular bisector of the wire, okay. On the other hand, when the wire is infinite in length, okay, the case 2, okay, the case 2, when the wire is infinite in length, what will happen? The case 2, when the wire is infinite in length, when the wire is infinite in length, what will happen? Theta 1 and theta 2 will be equal to 90 degree. So sine 90 degree, and this d you can consider it as the small letter r, okay. This d you can consider it as the small letter r. So in that case, when the wire is infinite in length, then theta 1 equal to theta 2 equal to 90 degree. So in that case, the total magnetic field will be B equal to, so here B is equal to mu naught I by 2 pi r into sine 90 degree, that will be equal to 1. Actually here I have used the letter D. Instead of D I am actually using R. Okay, there is nothing, this is nothing a major change actually. So mu naught I by 2 pi r into sine 90 degree, that will be equal to, sine 90 will be equal to 1. So mu naught I by 2 pi r, okay, mu naught I by 2 pi r. For an infinite wire, you have to use this equation, B equal to mu naught I by 2 pi r, okay. So when the wire is actually semi-infinite, okay, when the wire is actually semi-infinite means it is half of the length of the infinite wire, okay. So in that case, you have to actually divide this expression by 2. Then you will be getting mu naught I by 4 pi r. So that thing I will be writing here. When the wire is semi-infinite, that is the case 3. When the wire is semi-infinite, okay. In that case, the magnetic field due to this wire is given by B equal to mu naught I by 4 pi r, okay. As you can see here, it is 2 pi r. Here it is 2 pi r. This is 2 pi r. When the wire is semi-infinite means it is half of the length of the infinite wire. That means you have to divide the magnetic induction or magnetic field by 2. In that case, you will be getting mu naught I by 4 pi r. Here it is 2 pi r. On dividing, you will be getting B equal to mu naught I by 4 pi r. So this is how you can calculate the magnetic field for different cases of a straight wire. Okay. So all these things you need to prepare well, the different cases of the magnetic field due to a long straight wire. Okay. For different cases, you can actually memorize the formula or memorize the equation. That will help you to solve the numerical problems. Okay. Right. And the next thing is magnetic field at the center of a current carrying arc. Okay. Magnetic field at the center of a current carrying arc. That concept we can discuss now. Next concept is magnetic field at the center of a current carrying arc. Magnetic field at the center of a current carrying arc. This is the concept. For that, I need to draw an arc here. Let me draw the arc manually here. So this is the arc. And you have a point P at the center of this arc. And this is the current element DL. Okay. And the current I flowing through the wire is I. And this is how the point P is connected. This is d theta. This is d theta. This is the small portion of the wire DL. And the radius of the arc is given by capital R. Okay. The radius of the arc is given by capital R. That is this distance. This distance is actually capital R. is capital R. If the length of the arc is capital L, then what will be the magnetic field? So magnetic field is given by B equal to mu naught by 4 pi IL by R square if the length of the arc is capital L. Okay, mu naught by 4 pi IL by R square. So this is how you need to find out the magnetic field at the center of the current carrying arc. Okay. So for all the equations for finding the magnetic field, so when the coil or when the wire or coil, whatever it may be, when the coil or wire has n number of turns, then what you have to do is you have to multiply the field by n. Okay, let me consider that this wire has n number of turns. So this wire or this current carrying arc has n number of turns. Okay, n number of turns. In that case, the magnetic field is actually multiplied by capital N. So B equal to mu naught by 4 pi N into IL divided by R square. Like that you have to do. You have to multiply the total field by capital N. So this is how you need to apply or you need to multiply capital N with the magnetic field for whatever expression you are writing. Okay. So this is how we need to find out the magnetic field at the center of a current carrying arc. And one more thing I want to tell you, if the loop is a full circle, okay, this can be considered as a case. If the loop is full circle, if the loop is full circle, in that case, the magnetic field at the center is given by B equal to mu naught Ni divided by 2 into capital R. Okay, that means this loop is a full circle. Full circle means something like this. If the loop is a full circle and it carries current, it carries current I. Okay, and if you want to find out the magnetic field at this center, then you have to apply this equation B equal to mu naught Ni by 2R. Okay. And this is how you need to understand the concepts of magnetic field due to the current carrying arc. And the next thing is magnetic field due to a circular current carrying coil. Okay, magnetic field due to a circular current carrying coil. And that we will be discussing now. For that, I will be going for the next page. So magnetic field due to a circular current carrying coil. Current carrying coil at a point along the axis of the coil. So this thing we will discuss now. For that, let me consider a circular loop. Circular current carrying coil like this. And I am having a point P here from the center. The point P, and it is at a distance x from the center. Okay, it is at a distance x from the center. This distance is actually x. This distance is x. And the radius of the coil, it is taken as capital R. The radius of the coil, it is capital R. And I am considering a current element here. Here I am considering a current element of length dl. From here, this point P is at a distance small r. Okay. So what is the magnetic field due to the entire circular current carrying coil at this point P? Okay, what is the magnetic field due to the entire current carrying circular coil at this point P? So that I am going to write here. So B equal to mu naught by 4 pi into 2 pi r square into n into I. N is the number of turns in the coil. As I have told you, whenever the coil has n number of turns, you have to multiply the field. So r square plus x square power 3 by 2. Okay. So mu naught by 4 pi 2 pi r squared ni by r square plus x squared power 3 by 2. So here let me write x square so mu naught by 4 pi 2 pi r squared ni by r squared plus x squared whole power 3 by 2. This is the general expression for the magnetic field due to a circular current carrying coil at a point along the axis. Okay, this is the general expression. Here also we are having different cases. So for case 1, x equal to 0. Okay, x equal to 0 means this point P actually lies at the center. Okay, this point P lies at the center. Okay, when this point P lies at the center here, x will become 0 now, because x is the distance from the center of the coil. So when this point P lies at the center, x is equal to 0. So in that case, what is the magnetic field? It will be maximum. Okay, so B max is equal to mu naught Ni divided by 2r. Okay, mu naught Ni divided by 2r. So how did we arrive at this expression? So here you can substitute x equal to 0 and then you can simplify the entire equation. You will be getting mu naught Ni by 2r when x equal to 0. This is the first case. The second case is x equal to plus or minus infinity. Okay, x equal to plus or minus infinity. That means this point P is far away from the center of the coil. This point P is far away from the center of the coil. In that case, what will happen? Obviously, the influence of this coil will be very, very less at infinity. Okay, when you go very much away from the coil, then you won't be finding any magnetic field there. So that means the magnetic field will be very minimum, that will be equal to 0. Okay, so this is how you need to understand the concept. When you move far away from the when you move far away from the coil, your magnetic field will be 0. And then the third case is x is greater than capital R. That means this distance x is very much greater than the radius of the coil. In that case, what will be the magnetic field? So Bx is equal to mu naught Ni R square divided by 2x cube. Okay, 2x cube. And the fourth case is when your x is very much less than R. That means this distance x is very much lesser than the radius of the coil. So in that case, the magnetic field value will be Bx is equal to B naught into within the bracket 1 minus 3x square divided by 2r square. Okay. So here this B naught is nothing but the maximum value of the field. So that is nothing but this thing. Okay. So this B max is nothing but B naught. This is the maximum value of the field. Okay. So this is how you need to find out the magnetic field due to a circular coil carrying current. Okay. Okay. Then we shall apply the Biot-Savart law for moving charge. Okay, Biot-Savart law for moving charge we will be discussing now. So the Biot-Savart law for moving charge means the charge will be having some velocity. Okay. Biot-Savart law for moving charge. So here let me consider that I am having a charge Q. Okay. I am having a charge Q. So this charge Q is moving with the velocity V. Okay. Is moving with velocity V. Is moving with velocity V. And the point P is here. So this velocity is vector V. The angle between these two lines is theta. So in that case, what is the magnetic field? B equal to mu naught by 4 pi QV sin theta divided by r square. Okay, mu naught by 4 pi QV sin theta by r square. So this is the expression for magnetic field to moving charge. Then it is moving with velocity v. In terms of velocity, you can write like this. Okay. In terms of velocity, you can write like this. Okay. So then we shall discuss the Ampere circuital law. The Ampere circuital law we shall discuss now. And this Ampere circuital law is actually analogous. Okay, it is analogous to Gauss law in electrostatics or Gauss theorem in electrostatics. Can anyone tell me what is the significance of Gauss law in electrostatics? Can anyone tell me the significance of Gauss law? Does anyone know about this? The significance of Gauss law in electrostatics? Yes, students. Gauss law in electrostatic significance. Does anyone know anything about this? You can tell me whatever you know about this, no issues. Significance of Gauss law in electrostatics. Or the statement also you can tell if you know about that. Gauss law in electrostatics. What is the statement or significance here? Yes, students. Does anyone know anything about this? Okay. So actually, Gauss law is used to find out the electric field. Okay. Gauss law is used to find out the electric field, and it gives the relation between electric field and charge. the relation between electric field and charge is given by Gauss law. But Ampere circuital law, it is analogous to that. So this Ampere circuital law actually gives the relation between magnetic field and current. Okay, it gives the relation between magnetic field and current. Okay, so this is the comparison of Gauss law with this Ampere circuital law. And what you can do is, instead of using Biot-Savart law and going for some complicated calculations, you can apply the Ampere circuital law and find out the magnetic field easily. Okay, it is just a closed integral. This Ampere circuital law is given by a closed integral. So mathematically, that is represented like this: integral, actually closed integral, B dot dl is equal to mu naught into sigma I. Sigma I means the summation of the currents enclosed in a loop. You can take any loop. Okay, you can take any loop or any closed path in free space, and you want to find out the magnetic field due to the closed loop, then you can use this Ampere circuital law. And instead of applying Biot-Savart law and going for some rigorous calculations, you can use the Ampere circuital law and find out the magnetic field. Okay, so this is how you need to use the Ampere circuital law. Using the Ampere circuital law, easily you can do the calculation of magnetic field. Okay, so this is the significance of Ampere circuital law. Simplification of the formula for finding the magnetic field. And using this Biot-Savart law, you can find out the magnetic field of a long solenoid. Okay, a long solenoid. So, what is meant by a solenoid? What is meant by a solenoid? So, a solenoid coil actually looks like this. A current carrying helical coil. Okay, current carrying helical coil, and it can be used to produce uniform magnetic field for a long range. Okay, so here you have a conducting wire which is tightly wound over a cylindrical frame. So, okay, cylindrical frame in the form of identical circular turns. So, at any point on the axis of this solenoid, you can find out the magnetic field. Okay, you can find out the magnetic field. So, you can apply you can apply the Ampere circuital law and find out the magnetic field. So, integral, closed integral, B dot dl is equal to mu naught n I into L. Okay, what is meant by n? N is the number of turns per unit length of the solenoid. Number of turns per unit length of the solenoid. So when you multiply this number of turns per unit length into the length of the solenoid, you will be getting the total number of turns. So N into L will give you the total number of turns in the solenoid. I is actually the current flowing through the solenoid coil. So here you can see that the magnetic field just depends on the current, and what you can do is you can simplify this expression. Integral B dot dl will give you BL is equal to mu naught N IL, and B is equal to mu naught into N into I. This is the expression for finding the magnetic field due to a solenoid. Okay. So here you can see the magnetic field does not depend on the radius of cross section of the solenoid and also the average diameter of the solenoid. It is just equal to mu naught times the current enclosed by the solenoid. Okay. So this is the expression for magnetic field to a solenoid. Do you all understand this concept? Students, do you all understand this concept?
Yes, sir.
Okay. Then we shall move on to the concept of toroid. Okay, the concept of toroid. The magnetic field due to a toroidal solenoid or toroid. Magnetic field due to toroidal solenoid. It's otherwise called toroid. So what is the meaning of this toroid? It is actually a bent. If the solenoid is bent in a circular shape and the ends are joined, then we will get a toroidal solenoid. Okay. So it looks like this. So here you will be having wire, okay, wire wound over the solenoid, okay, like this. The wires will be wound over the solenoid. It's actually looking like a solenoid bent in circular shape, okay. A solenoid bent in circular shape. The wires are actually wound over it. So it is made up of a coil of insulated or enameled wire wound on a donut-shaped form made of bowled iron. Okay. So here current is flowing. Okay. I have actually shown the current direction of this toroid. So inside the toroid, the magnetic field is non-zero. Okay. Inside the toroid, the magnetic field is non-zero, but all the other points, the magnetic field is zero. So this is how you need to understand the concept of toroid. And we will be writing the expressions or magnetic field. So before that, we should know the radius of this point. So from here to here, it is R1, and from here to this point somewhere, it is R2. Okay, so this is R2. This is R2, and this red color distance is actually R1. Okay, this is R1. So the expression for the field that points in the open space. So case 1, when R less than R1, that means in the open space somewhere here. Okay. So in the open space somewhere here, what will be the magnetic field when R is lesser than R1? What will be the magnetic field? That magnetic field will be 0 here. Okay. Magnetic field B will be 0. Somewhere in this open space it is 0. And inside the toroid, okay. The second case, inside the toroid. That means your R is greater than R1, lesser than R2. That means somewhere here, okay, in this portion, inside the toroid. So in this portion, you are considering some point and finding the magnetic field. What is the value of that magnetic field? So that I am going to write here. So B is equal to mu naught Ni by 2 pi R. So inside the toroid, mu naught Ni by 2 pi R. Mu naught Ni by 2 pi. So inside the toroid, the magnetic field is actually inversely proportional to R, as you can find from this equation. So instead of 2 pi R, what you can do is you can consider that the average length is capital L, and you can write L here to find out the magnetic field. Okay. So this is the second case, and the third case actually for any point outside the toroid. Okay. For any point exterior to the toroid, the magnetic field will be 0. Exterior to toroid, the magnetic field will be 0. So this is how you need to find out the magnetic field for a toroid. And let us keep it this much for this session. And we shall continue our discussion on this moving charges and magnetism in our next class. Okay. Thank you so much for joining the session.
Thank you, sir.